I'm Trey Walters. I'm the president and founder of Applied Flow Technology. And my topic today I'm going to talk about is steam hammer load analysis and how they're not as safe as you think with common methods, and how some improvements to those methods. The webinar here is based on two papers that I presented last summer at the ASME 2022 Pressure Vessel Piping Conference in Las Vegas, Nevada. And there was part one and part two. These are the titles. The paper numbers by ASME are given here. We have copies on our website, and if you want to review those and get all the nitty-gritty details, you can. There's a less technical, more popular level summary that you can read about in the on an article that is actually on the ASME website. So I'll go to the next page, and you'll see here, these are the two papers that were presented last year. Over here on the right, there's a, at that web address, there's actually kind of a 1,000-word kind of summary of some of the things that we're going to talk about today. Okay, so we'll do part one. First we're going to do is we're going to critique steam hammer load analysis methods, and then part two is actually going to be quite a bit shorter. So let's start off here, and we're going to talk about the good news and the bad news, and we're going to start off with the bad news. The bad news is that forces from steam hammer in nuclear fossil power stations have been significantly underestimated for the last 40 years. Nuclear power plant steam piping that uses these common methods is not as safe as most people believe. But the good news is that new methods and tools have been recently developed which will more accurately and conservatively predict loads on steam piping. The tools we're talking about more specifically is a new tool that we released a couple of years ago called xStream. It's currently on version 2. And then also the good news here, my last thing is thank goodness for safety factors that were used on previous designs that helped keep those still working with hopefully without any significant issues. But there are safety issues there that we recommend, and I will at the end people go back and look at that. This is a, on the right here is a screenshot that I have shamelessly taken from a paper by Ben Robignati and Gray, who have published a paper at the PVP 2015 conference, and there's the reference right there. So they had this graphic in their paper in 2015, and basically it just talks about what goes on in this case, like a nuclear power plant, where you have steam coming off your steam supply, going on through some longer pipes ultimately into turbines, and then down here you have turbine stop valves. And when there is some sort of a uncertainty condition, that the goal is to close these stop valves as quickly as you possibly can to protect the turbines. Typical closure times are effectively about 100 to 200 milliseconds. They actually have longer closure times, but the times that actually drive the steam hammer waves is more like 100 to 200 milliseconds. When that happens, it sends a pressure wave traveling at near acoustic velocity back towards the steam supply. So there's going to be a wave generated at these valves going to travel back to the piping towards the steam supply, and any elbow pairs that you have in here are going to see forces. Those imbalanced forces from this transient, the structural supports need to handle these, and this is often called a steam hammer. So some background. The work in this paper is derived from two occurrences. One is there were 4 papers at ASME PVP conferences in 2014 through 2018 from multiple authors which questioned the conventional method based on the work of Goodling, who he himself published a paper back in 1989 at a PVP conference. And his method, which was certainly an improvement at the time, is something that we're going to show today is not as conservative. People thought it has been conservative over the last 4 decades, and it's really not conservative, and we're going to talk about why. The other development is the new commercial simulation tool, xStream, which was in early 2021, designed to simulate specifically transient compressible flow, including steam hammer. And then also there was another paper that was supposed to precede the 2 papers at the 2022 Power Conference, and it got delayed by COVID a couple times. It still hasn't been published, and so It's called How Fast is a Finite Gas Transient Wave and Why Does It Steepen? I'm a first author on that. That's going to be published at the PVP conference this year. It's going to be in Atlanta. So that paper was supposed to come before these ones, and just because of conferences being rescheduled and canceled, it's coming out after. Let's talk about acoustic wave behavior and steam flow, and just the physics of an instantaneous wave. So before considering the flow of real gases with friction and heat transfer, let's make things simple, and we're going to consider a case with a perfect gas, adiabatic flow, frictionless horizontal pipe. So you've got flow coming in here from point 1 to point 2, and there's a valve, and what we're going to do is we're going to close that valve instantly. Okay, so what happens to the gas flow right now? We're not even to steam yet. We've got a perfect gas. Okay, so what happens with the physics? So this idealized case has constant thermodynamic and fluid dynamic properties everywhere because it's frictionless. There's a velocity v and a speed of sound c. And assume the valve closes instantly at t equals 0. There's two waves that are generated that travel upstream and downstream of the valve. Upstream of the valve is a compression wave. That compression wave is traveling against the direction of the bulk fluid flow, the gas flow, and it travels at a velocity of v minus c. C is greater in magnitude than v, so this is actually a negative number, but our coordinate system up here has x going from left to right, so this is going to be a negative wave speed, and it's equal to v minus c. There's another wave which is generated, and that's downstream of the valve. That's an expansion wave, and it travels at v plus c, and that travels to the right. So those two waves are generated, and they travel down, and in our case right here with perfect gas, adiabatic, frictionless flow, horizontal pipe, they travel at a constant wave speed, both to the left and to the right. So let's dig into this a little bit more. So we just talked about this. What we're going to focus on right now is more on the compression wave, because that's the one that causes issues with forces on the elbow pairs. So let's go ahead and take a case where we're going to look at time, and we're going to look at distance x along the pipe, and we're going to look and see what the waves are. Oh, actually, we're going to look at, okay, here we're going to look at both waves, going at compression and expansion. Later, we're going to focus on just the compression wave. So what happens is, this is an instantaneous wave, and so the wave actually travels in time over this distance from left to right, and it travels at the slope here is the wave speed, and it's v minus c. Now on the right, it is a different slope, and it's traveling at a higher wave speed, which is v plus c. So that's how it travels, and that's how the direction of those two waves. So now let's move from an instantaneous wave when we close the valve instantly to a finite duration compression wave, which is what happens when you have a valve which doesn't close instantly, but it closes over some finite amount of time. Okay. When that happens, there is actually not a single wave which is generated, but there are a family of waves. What do we mean by a family of waves? Okay, so we're going to talk about it here. So we're going to talk about the upstream of the valve now, and we're not going to worry anymore about the downstream of the valve. Upstream of the valve, we're going to close this valve, and it's going to close, and it's been shown by others in the literature that it tends to be roughly about a constant velocity versus time, fairly linear, and constant flow rate versus time. Okay, so we're going to assume that this valve closes in such a way that the gas velocity goes from the initial steady state velocity at the valve, and it's going to close over some time tc, okay? And then the valve is completely closed. So let's look at what happens. So we're going to introduce two new subscripts here, F and B. F represents the front of the wave family. This is also the steady state conditions, SS, okay? B represents the back of the wave family. So at t equals 0, just when you get your before the valve closes, there's no waves being generated here, okay? Right when the valve initially just starts to have its first incremental movement, closure, and there's a change in velocity, there's a wave which is generated, and it travels up the pipe back towards the supply conditions, okay? And that wave travels at the initial velocity v minus the initial sonic velocity c. That's the slope of that line. at some other time, let's say at half the closure time divided by 2, we can see the velocity here is going to be about half the steady state velocity, and there's going to be a wave generated at that time. But actually, between the blue and this orange wave, there's a whole bunch of waves. Every moment that the valve incrementally changes, there's another wave which is generated. And then finally, when the valve hits its closure point, a final wave is generated, okay? And we're going to say that's at t equals 2c. That thing to note here is that the slope is different. There's a different slope on the green wave than the blue wave. That's continuously varies in between from the time equals 0 to time equals the closure time. Okay. Now this slope is equal to the velocity at the back of the wave, VB, minus the sonic velocity at the back of the wave. Okay. So, a pretty easy thing to look at here is that if the valve is closed at t equals c, what is the velocity of the gas? And that answer is pretty easy. That is 0. With a closed valve, there is no velocity at this point where the valve is right here. Okay, so then the slope is just equal to the minus sign of the sonic velocity b. That's a different sonic velocity than at the front of the wave, because there's already been compression happening. The temperature is different. The pressure and temperature is different along the green line. Okay. You can see here at this time t equals tc. At that point, that's just where t sub c is. And then also in between these two right here, this area between the first wave when the valve first starts to close and the final wave when the valve fully closes, this is what we call the wave family. And as the valve closes all throughout its whole process from being fully open to fully closed, it's generating a whole bunch of incremental waves. And each new wave is traveling into the waves that were previously generated, and that becomes the wave family. So everything that's actually happening here that's interesting happens between the blue and the green lines. For a perfect gas, an adiabatic frictionless flow, and a horizontal pipe, all of these parameters can be calculated analytically. So what happens when this wave is traveling down a pipe and it goes through, for example, like an elbow pair? So let's take a case right here where you can see at the top, we have, this is a case where no transient has happened. So there's steady state fluid velocity V. It's constant because we're talking about no friction case. So it's constant velocity. At this elbow pair up here, the velocity is just equal to the steady state velocity, and the pressure is equal to steady state pressure. Same thing down here at point 2, okay? And there's no imbalanced forces. At some certain time, the valve closes instantly. It's somewhere downstream, and it's generating a wave which is traveling back towards the source. This is the acoustic wave. It's traveling at V steady state velocity minus the steady state sonic velocity C. Okay. At this point in time, this gas on the right has been brought to stop. V equals 0, and the pressure is now at a high pressure. Okay, and so this higher pressure here is generating a force, and it's pushing this assembly between these two elbows. It's pushing it to the right because there's higher pressure here than here, and so there's a force that pushes it to the right. And that force can be predicted. And so with the force versus time profile, you can see is when the wave first enters into the first elbow pair, the force goes up. Okay, and that force is not exactly equal to, but roughly equal to on a first approximation. The high pressure minus the steady state pressure down here, the pressure difference times the area, okay? And then eventually the wave makes its way all the way through the second elbow pair and goes all the way out. And both sides, both elbows are at the high pressure because, again, this is all frictionless, and so there's no more imbalanced force. So what happens is the force comes back down, and you're left with a force versus time profile that looks down here in the lower right. All right, so we've created a little video that kind of shows what happens as the wave moves through. So I'm going to play this video here. I think I need to change my pointer options here to turn off the laser pointer. Okay, so what you're going to see is initially there's some flow going through. The valve closes, the wave comes in. As the wave goes through there, it causes those elbows to move. And at first it pushes it to the right, but then what happens, there's a reaction because of the elasticity in the system, and there's the elbow pairs move back and forth. Now that they're going to move unless they're restrained. If they're restrained, there's not going to be any movement, but the restraints that are put there have to take that load, whatever that load is. So the question is, what is that load, and how high is the force, and what does it look like over time? That's what that's really what we're trying to get at today. So we're going to go on, and if the wave is an instantaneous compression wave, so the valve, downstream valve, closes instantly, then the shape of the force versus time profile looks like this. It's like a step change, like a square wave, okay? Now, that's an idealized case because there aren't any valves that close instantly. So you have a finite duration compression wave where the valve closes over some time, and it looks more trapezoidal like this, okay? So this would be when the first part of the first wave of the wave family reaches the first elbow right here. The force starts to go up, and then it reaches a peak, and then it comes back down, and then this is the point where the back of the wave family passes through the back of the elbow pair over here, and you get a force profile. So this is more realistic, and then the question is, how do you estimate this or predict what this looks like, and what's the peak force? That's what you care about, right? So the traditional method is Goodling's method, who was a smart engineer back in the 80s who worked at Gilbert Commonwealth in Pennsylvania. Today, that company is now Worley, owned by Worley in Pennsylvania, and the way that the Goodling's method works is that you estimate a maximum force using a Joukowsky pressurized approximation, okay? So what you do is you assume the valve closes instantly, you get a Joukowsky pressurized delta PJ, you multiply it times the area, then you put a 5% fudge factor on, and that is the maximum force, okay? Then you calculate something called the characteristic length. That is based on the steam acoustic speed, C. So it's the sonic velocity, the acoustic velocity of the steam, okay, and at the steady state conditions. And then you take the valve closure time, T sub C, you multiply those and you get something called the characteristic length. You calculate the maximum force on a pipe run leg based on its length. So you have two elbows here. The length in this leg, we call leg 1, 2. The length is L sub leg 1, 2. So that's the length. So what you do is you take this F max up here in step 1, you multiply it by the length of the leg, you divide it by the characteristic length, step 2, and that becomes the maximum force, okay? And if the leg length is greater than the characteristic length, then the maximum force on this elbow pair is just equal to the maximum force. If desired, it's possible to estimate a force versus time profile that looks like this. And if you go back and look at Goodling's paper back from 1989, he described a step-by-step way of how to do that. Okay, so how do you, rather than use kind of a relatively simple, straightforward algebraic form like we just talked about, if you want to get at this more detail, how do you do it? Okay, so simplified method is to assume adiabatic, frictionless, perfect gas, horizontal pipe flow, okay? Steam doesn't really behave that way, but let's assume that it does. If that is how it behaves, then you have the equations of mass conservation, which is pressure versus time, and how it changes over distance with velocity. This is the density of the steam or the gas. This is the sonic velocity, and those have to balance to 0, okay? Then you have momentum conservation. You can actually do a closed form analytical solution on this and solve for all of the flow field at any point, any location, any time using these two equations right here. But it's very simplified, okay? So what does a more realistic solution look like? The more realistic solution is we have to bring in more variables here. So now we're talking about real gas, like steam behaves as a real gas. We got friction, we have heat transfer, and the pipe can be sloped. Okay, so that complete method now accounts for everything within these assumptions. And these, you end up with 3 differential equations here: mass conservation, momentum conservation, and energy conservation. Now, the form of these equations can be represented in different ways. And this particular form is a really convenient way that was published by Fred Moody back in 1990 in a textbook that's referenced in these papers. And it's a very convenient formulation. But the only way to really solve these practically is to have a numerical solution. That's the only option. And that's what AFT xStream does. That actually solves all of these equations without any without leaving anything out fundamentally. So all of the fundamental principles here are included in the solution, okay? So I found out something real surprising a few years ago when this basically is almost exactly 2 years ago. It was in early 2021. I was doing some beta testing on AFT xStream before we released it commercially. And I was looking at this problem that Ben Rovagnati and Gray published back at the ASME conference in 2015, and the paper number here. This is all basically all the different parameters that they had in their paper, okay? But the basic gist is that there's a pipe, this is the turbine stop valve right down here. This is the steam supply. Steam supply is at 1,000 PSI. I'm gonna talk it in terms of English units, but we've got metric equivalents for everything here, so you can see that if you want to look at that, okay? So the turbine stop valve, and we're gonna say the turbine stop valve closes, and it closes in 100 milliseconds. And that's what was part of the problem statement that Rovagnati and Gray put forth. And then along the way, there's these green stretches where there's elbows that are basically they're 40 feet length on the elbows, and there's longer stretches in between. And so there's actually 7 elbow pairs that we're going to look at. The elbow pair that's right at the steam supply, and then further distances out, all the way out almost 2,000 feet away, or 1,980 feet away. Okay. Here's the other conditions you have here. The pipe is a 30-inch nominal diameter pipe. Roughness, temperature, it's just barely above saturation. The flow rate is given here, and other parameters like what's the steady state velocity is 116 feet per second, et cetera, sonic velocity. Okay. The wave speed at the front of the wave is VF minus CF, and VF is here is the 115 feet per second. C is the sonic velocity is 1640, so it's actually is 1,498 feet per second at the front of the wave. The back of the wave is the minus of the sonic velocity at the back. And you can actually figure that out to be 1,632 feet per second. So you can see the back of the wave here has a higher magnitude velocity than the front, and that's why the back of the wave catches up with the front. So this is what it looks like if you do a numerical solution, okay? So the numerical solution here, this is where the turbine stop valve is down here. Here's the steam supply. And we're gonna look at what happens when you close this turbine stop valve over 1/10 of a second, 100 milliseconds. The very first wave is gonna travel along the blue line. The back of the wave is the orange line. And this comes out of a numerical solution with AFT xStream, solving all of the real gas friction equations, okay? Here's the leading edge of the wave. This is the back of the wave at t equals 0.1 seconds. And so those waves travel, and that orange wave travels at a different slope. And it's actually, you can see as you go further out in time and down the pipe towards the supply, you can see the back of the wave position is catching up with the front. Okay, this initial characteristic length that you can get just basically subtracting what happens at 0.1 seconds is about 150 feet. You can see the characteristic lines shown right here. And but the important thing to see is that the orange line is catching up with the blue line, and that means the wave is steepening. Okay, so and so that has implications for the forces we're going to talk about. Okay, with AFT xStream, you can figure out what is shown here on this slide here, is that if you take the velocity at the front of the wave family, you can see right here, this was the initial velocity, it was 1,498 over time. And as the front of the wave family moves back towards the supply, you can see it actually speeds up a little bit. This is with a perfect gas type solution, frictionless, it stays the constant. But with a real numerical solution like you get from AFT xStream, you can see how it actually speeds up a little bit. Okay, the back of the wave family starts off at about 1,630 feet per second. You can see that it slows down. Okay, but you can get these actual parameters out of software like AFT xStream. Okay, what you can also do is you can take what I just showed you on the previous slides. Oops, I'm going the wrong way. I'm going to go back. You could subtract the positions here that you get out of the wave velocity, and you can actually say what is the distance between the front and the back of the wave. And at 0.1 seconds, when the turbine stop valve fully closes, you can see that distance between the back of the wave and the front is about 150 feet right here. Okay, 150 feet. But what happens is because the back of the wave is catching up with the front, as you go forward in time, the distance between the back and the front shrinks, okay? And so finally, you can see if you go out far enough, the back of the wave will catch up with the front of the wave, and it becomes basically a vertical, like a vertical shock wave. What this tells us is that the whole idea of characteristic length, which assumes this 150 feet is constant, it's a flawed concept, and the engineering community should discard that concept. There is no characteristic length. It does not exist. There's an initial length between the front and the back of the wave, but as time goes on, the back of the wave catches up with the front, and there is no characteristic length. There's a changing distance between the front and the back. And so you can also see this in here in a numerical solution from AFT Xtreme. Okay, so if we look at the first elbow pair right here, and then you plot the pressure versus distance, you can get this pull out of a solution from Xtreme that looks like this. The elbow pairs right here are the front and back of these different elbow pairs are these magenta lines right here. So the question is, how much of the wave between the front and the back of the wave family fits inside these elbow pairs, the two magenta lines, okay? So we're gonna go on in time. At t equals 0.1 seconds, that's when the turbine stop valve finally closes, and this is where the wave position is right now. And what's causing the force right here in this part is what's happening between these two magenta lines. That between the back and the front, that pressure difference is driving the force. You can see as you go through in time, now the wave is up here at this elbow pair, and it has what's driving the force is the difference between the front and the back right there. As you go down in time and you look at each new elbow pair, you look at time, and now we're going to go here, we're going to go here. What you can see is the more and more of this wave is fitting inside this 40-foot length between the front and the back of the wave family. And if you get all the way down to this final elbow pair, the entire wave is inside that the elbow pair, okay? Because the back of the wave is caught up with the front. What that means is the force is much higher. So we can look at what those forces look like. I'm going to play you a quick animation here. This comes out of Xtreme can make this animation for you, and I'm going to go ahead and play that for you here real quick. So this is what happens with the pressure. Here's in PSI. This is kilopascals on the right over the entire distance right here. You can see, and time is up here at the top in milliseconds. And you can see as this wave goes down, you can see how it's just getting steeper and steeper and steeper. And that's just because the back of the wave is catching up with the front. All right, so let's go on from there, okay? Now you can come in and look here at the what's going on with the forces. And the interesting thing that you see is that the forces on leg one, which is the first elbow pair, that's about 15,000 pounds force and about something like about 60 kilonewtons, okay? But what happens is because there's more and more of the wave is fitting in each leg 4, leg 7, leg 10, all the way to the end, the force gets higher and higher, okay? And so the interesting thing here is that Goodling's method, which, you know, it was developed 4 decades ago, but it predicts all of those forces for all of those 7 elbow pairs should be the same. And you can see that the elbow pairs, as you get further and further away from the source, are much, much higher than Goodling would predict. That's why we're saying that Goodling's method is not a conservative method. And if you've used Goodling method in the past, you're using it today, you're not getting conservative results, okay? These are the force predictions of these peak forces in here in a table. So this is just the forces for leg 1 all the way up through 19. This is the percent of Goodling, okay? And so you can see that the forces on the final leg out here, leg 19, are over 3 times higher than Goodling would predict. Okay, and so that's a little bit concerning. There is some sensitivity to how you do computational sections in the AFT Xtreme model. And so what you see here, as you add more sections into the pipes, what happens is the peak force that you get increases. And so really to get the peak forces that you're seeing here, you need to use even more sections. And so when Ravignati and Gray did their paper back in 2015, they only used 40 sections and they didn't do a nodal sensitivity study. So they were showing, you know, higher forces. But actually the story is even worse than Ravignati and Gray presented back in 2015, because if you put more sections in the numerical model, then you get even higher forces in here, okay? So be careful if you're ever using numerical methods on here to make sure you're using enough sections, okay? So how fast do the waves steepen? This is another way of asking how much faster is the back of the wave than the front. We looked at this chart earlier of the front of the wave family and the back of the wave family. The difference in speeds decreases over time in this example. Goodling assumes this difference is negligible. Here it can be seen that the difference is initially right here is about 134 feet per second. So this is another way of saying that the back of the wave is catching up with the front at 134 feet per second. It could be shown that this speed can be estimated from this equation here that we develop in our papers, that I develop in our papers, and using the initial velocity of the steam of 116 feet per second, a gamma value of 1.25 for steam, you get an initial velocity with this equation of 130 feet per second, which is pretty darn close to the 134 that comes out of the full numerical simulation. This simple equation right here tells you how fast the back of the wave is catching up with the front. So some fundamental problems with Goodling's method that have become clear in recent years is that it tacitly ignores wave steepening. It doesn't acknowledge that it can occur, and it assumes that the forces on the pipe run lengths are the same regardless of how far the elbow pairs are from the source of the transient. It actually miscalculates the characteristic length because it uses acoustic velocity C, and it should be using the wave velocity A. So that was another, it's typically a difference of about 10%, but that's another problem with Goodling's method. It uses an incomplete force balance based only on pressure differences, on the pressure between the elbow pairs. And there's other parameters that go into that. And if you care about that, we have other webinars that we have taught and papers that talk about how to do a complete force balance. AFT Xtreme does a complete force balance. There's not leaving any terms out. It also misestimates the force versus time profile, magnitude, and duration. What did Goodling miss on wave steepening? What did he ignore? The relationship for how fast a wave steepens is roughly given by this right here. Sonic velocity at the back of the wave minus the sonic velocity at the front plus the initial fluid velocity, just the bulk velocity, about 130 feet per second. Goodling and others afterwards, what they did is they estimated what this value was, and what they did is they ignored VSS in here, and they only took the difference in sonic velocities. And that's like 14 feet per second, which is really slow. So they said wave steepening is just not very important because it only happens at 14 feet per second. But if you actually put to get in the full estimation of what the change in the wave velocity and how fast it steepens, it's actually 130 feet per second, it's like 10 times as high. So wave steepening happens 10 times as fast as other people have estimated, and that's why this has really kind of been missed over time. So conclusions on part one. Goodling method is not reliably conservative. It should not be used for steam piping load estimation, except maybe if you have very short pipe runs and there's not enough time for wave steepening to really have an effect. Going forward, engineers should consider using a capable simulation tool such as AFT Xtreme to determine peak loads and load profiles. Engineers should take care to check peak forces and nodal sensitivity. So don't just believe what comes out of a model in the simulation. With Xtreme or any other software, make sure you check nodal sensitivity. For quick preliminary force estimates, an alternative method should be considered, which includes wave steepening effects. I'm going to talk about that in part two. Existing systems designed using Goodling are not as safe as believed, and we would definitely recommend that existing systems should be reevaluated with some of the new things that we're talking about here today and in the papers from the PVP conference last year that I published, and that they should be strengthened where they realize that they were not as designed with appropriate peak forces. And that's what we would recommend to the entire world that has used Goodling. To design their estimate forces and to design their pipe system and the pipe restraints, is that they might have underestimated those peak forces as you go look at it again. Okay, so part two is an improved method of estimating steam hammer loads. So if you want to get the full correct answer, AFT Xtreme can do that. If you model it properly and you check nodal sensitivity, it can do all the real gases, heat transfer, friction, all that. It can do all that, okay? But there are some ways that are better than Goodling that you can get an estimate on that. And it's a pretty quick algebraic form, okay? A little more complicated than Goodling, but much better at handling wave steepening. So I actually developed this last year and published it in the other paper, this improved method. I'm gonna talk about how the improved method works, okay? Let me see here. Okay. So first, recommendations on predicting steam hammer loads. There's many variables that can influence steam hammer wave propagation and imbalanced forces. Okay, it's highly recommended that if you want to get it right, you use a capable simulation tool such as xStream, which can simulate wave steepening, simulate other behaviors such as wave reflections in your system, and it can calculate a complete force balance. Engineers may still benefit from a simplified method, which is, okay, great. We don't have time to go look at everything with xStream. We only have some bandwidth. Is there any way for us to get some quick estimates? Okay. Be very careful with any algebraic equation to simulate it because it's a very complicated thing to try to calculate and simulate. Okay. So I'm going to give you in the paper gives, and I'll talk about today, a better algebraic way than Goodling. That at least everything that we've checked so far, it looks like it's conservative and is really useful for preliminary design purposes and screening whether wave steepening, how important it might be in your system. Okay, so I wouldn't trust it for a final result, but I would definitely recommend it as a preliminary tool. So the paper, which is the part 2, develops this method. Okay, so in general, in a piping system, let's say that you have waves and flow traveling throughout your system. This particular system has a valve in between. There's a diameter change, okay? If you want to do a complete force balance here, then you need to look at not just the pressure force here and the pressure force here, the momentum change that happens at a diameter change, the pressure forces that happen across, like for example, any type of a pressure loss, like a valve or something else that causes a pressure loss. Excuse me. There's friction forces also on the piping, and that contributes to the force balance. And there's also momentum change at the beginning and the end. And if you account for all those things, you've accounted for everything. Okay. Most methods don't account for all that. You can actually get a complete force balance if you go back to the fundamentals of Newton's second law, F equals ma. Take F equals ma, apply it to a piping system and elbow pairs, and you get an equation that looks like this. Okay, so pretty involved differential equation, but we can do some things to actually solve for this. Okay, we can evaluate this equation by considering each component force individually. Okay, that would be the forces at 1, 2, 3, and 4. So you get at the first elbow pair, you get a force that is due to the pressure, and you also get a momentum change, m.1. Then you have a force that's due to the friction on the piping, on the pipe walls, okay? And this is all stuff we're only calculating in the x direction. X is positive going from left to right. So we're only, at this moment, we're only talking about forces in the x direction. So you have that force. That is basically all the frictional resistance times m dot squared. And summing that up, you know, it is a continuous function. If we break the pipe up into discrete elements, we're going to add up all of these contributions from all the discrete elements from 0 to n. Okay, that's the pipe sectioning. Then there are pressure changes and momentum changes across the valve. You have to account for that. There's more friction in the downstream pipe. And then finally, there is pressure at the end elbow and momentum change there. Okay, that's something that we now call the component reaction method. We use this in our AFT Impulse water hammer software, but it actually was kind of complicated to actually use this formulation of Newton in AFT xStream. So we did something different. We did something that we call the acceleration reaction method. You can evaluate Newton's second law by directly tracking fluid acceleration during transient. There's a different way of drawing basically essentially a control volume. If you draw a different control volume, then you can get the same exact force, but by only tracking acceleration changes, which is the change in m dot over delta t times the distance step of the pipe section. So basically what we're talking about is what are the mass changes with time in each computing section from 0 to n in the beginning pipe and the end pipe. And if you add all that up, you can get the same exact force. We can show that you get the same force as doing things in the first method, the component reaction method. Okay, so be careful only using P times A loads. Be careful with that. Often it's approximately true, but not always, and it can be very incorrect. So if you use this method, this is what you're doing. Down here on this, on the lower part of the screen here, this is a complete statement using the component reaction method, the first method I talked about. of the force balance. And you're going to ignore all of these terms, and you're only going to pay attention to the pressure at A, P1A1 minus P4A4. And you're going to neglect everything else. It turns out that in a lot of cases, a lot of these terms are negligible, but they're not always negligible. And sometimes they can be really important, and you can be really, really off if you neglect them in some cases. So you got to be careful about that. And we would recommend you just don't do that. Don't use P times A, okay? So this was the Goodling method we talked about in part 1, okay? These were the forces I talked about in part 1. We already looked at all this, okay? What can be retained from the Goodling method? In this new improved method that I propose, and I proposed in the PVP paper from last year, we're going to keep the general idea of characteristic length, but we're going to rename it and treat it as a variable and not a constant. We're going to only use pressure forces to determine forces, okay? Because we're trying to get a quick approximate method, and pressure forces are often the dominant forces. They're not always. So this is not always going to be, this is just an estimate, okay? It's a quick estimate. We're going to continue to use the Joukowsky equation to determine maximum force, and we're going to construct a force time profile based on the length of the pipe run and wave speed. Okay. So we looked at this earlier with a finite duration compression wave, and it turns out if you let these waves go out long enough, this is the front of the wave family. This is time on the y-axis, x on the x-axis, distance x. Here is where the valve is, right here. That's the location of the valve which closes. It closes over some time. We'll call it 0.1 seconds, 100 milliseconds. This is the front of the wave family. Path of front of wave, path of the back of the wave. And if the pipe is long enough, the green line is going to catch up with the blue line, okay? And form a shock wave. We're going to call that distance x shock, and we're going to call that time t shock. And if this happens to be frictionless, if you can just assume for the moment that we're going to look at frictionless adiabatic flow of a perfect gas in a horizontal pipe, you can get analytical relationships that look like this. For what is the time to get to t shock? What is the distance from the valve to the shock wave, okay? So this is what we looked at in the part 1 with, so again, here on this slide, 38, this is an analytical solution for the frictionless adiabatic flow, perfect gas, etc. Okay, and then and these lines are linear. Okay, now if you do a real gas simulation, this is what comes out of xStream. These lines, they appear to the eye to be linear, but they're not. They're slightly nonlinear, but we can still use this to our advantage. This is a slide from the first part where what we talked about is what is what traditionally has been called the characteristic length, which is the distance between the back of the wave and the front of the wave family. Okay, so we're changing that name and we're calling it the length of the wave family. Okay, and you can see this is an analytical solution that of what coming from xStream. I'm sorry, it's not an analytical solution. It's a numerical solution coming from it to xStream. That's the blue line. Okay, and you can see how it is approximately linear, but not exactly linear. Okay, so I'm not going to get all the details of this, but you can actually go in and using all initial conditions, everything in steady state. Okay, this is the wave speed A during steady state and the closure time of the valve. You can come in and apply these algebraic formulas, which are a little more complicated than Goodling, but this is not that complicated, okay? And you can get another line to approximate the blue line. And if you do that, this is what it looks like. Blue line is AFT xStream results. The method that I just showed on the previous page is linear. So it's approximating this blue wave family length with the red line. And you can see that's not a bad approximation to that. And so you can calculate this red line approximating the real nonlinear behavior with this linear red line, and we can use this to estimate forces. So the new method that I proposed in the paper is that you get Joukowsky's equation again, which is the density of the steam times the sonic velocity and the velocity change. That's delta Pj. You get a maximum force. This is really the same thing as Goodling, except Goodling puts a 5% fudge factor, and we're saying we don't need a fudge factor because we're going to account for the wave steepening. So we're going to take the delta P, the Joukowsky pressure, right, delta P times A, that gets a maximum force. We're going to get a maximum force on each leg. but it's based on the distance from the source of the transient, okay? So this is now a variable. This is not a constant, because this leg, this wave, the distance in the wave family length is what we call it here. It is a function of time and distance on here, okay? So this F leg is going to change. The length of the leg might be the same 40 feet as you go down, but this wave family length changes according to this, what we showed previously, okay? You can get force versus time profiles estimated with this new method, new improved method, okay? And the blue is basically just take the F leg times the max times the length of the leg divided by this wave family length, which is different at each location. And then this is if the length of the leg is different than the wave family length, it's less. This is if it's equal, and if the length of the leg is greater than the wave family length. And you get these leg force versus time profiles out of these different shapes, okay? Now, if we go look and we compare this improved method, these are these dashed lines with the little squares. And then the colored lines comes out of an AFT xStream simulation, which is a lot more accurate. The interesting thing here is that Goodling, again, assumes everything, all of these forces are about 15,000 pounds force, about 60 kilonewtons. AFT xStream says that they get bigger, and this improved algebraic method I just showed you, you can see that it's approximating this, and it's a little bit higher in most cases. So out here is about 20% higher, but at least it's conservative, unlike the Goodling method, which is not. So it's not great, this method. It has a lot of assumptions in it, but at least it's better than Goodling. So highly recommend you don't use it for final design, but it is a preliminary algebraic form that you could use. Okay. So the simulation results we talked about already in here, and so the method, that the algebraic method that's proposed, this we call it the improved method, compared to the simulation results, you can see on this first wave right here, it's about 7% higher on the forces, but as you go through legs 4, 7, 10, and 13, it's not that much higher. Where it's really quite a bit higher is out here at leg 16 and leg 19. It's like 20% higher. So at least in this example, the forces get are over predicted. The improved method that are presented in the paper, and I presented here today, are higher in some cases by up to 20%, but at least it's conservative. Okay, so conclusions from part 2. A new method of estimating steam hammer loads is proposed today, and also was in the ASME PVP paper from last year's conference. It's more conservative than previous methods such as Goodling. It appears to be more conservative than AFT xStream simulation results, but not excessively so. But we haven't tested this out on that many things, so we can't say this is always true. Everything we've looked at so far, it is, but you can't count on it always being true, which is why you got to be careful using this improved method as a final design. The new method is recommended as a replacement for the Goodling method. We would recommend people don't use Goodling anymore. Use the improved method. It's going to be more conservative. The improved method does make many assumptions and should be used with great caution. Use it for preliminary design, not for final analyses. And for actual design loads, you really should use a tool like AFT xStream because it's going to give you the right numbers and you're not going to have any assumptions built in there. So that is it, what I have for today. If anybody has a question you want to throw in the chat real quick, you can take that, and I'll try to answer them. I don't see anything in questions right now. Oh, somebody did post a question. Sorry, I just see that. Actual valve closure. See if I can stretch this out and see it better. Yeah, not used to using the tool here. Maybe longer. Do you have any approximations or results to show that 200 to 500 milliseconds versus 100 milliseconds? This could be a recommendation. Yeah, there's a paper, and if you want to email me, TreyWalters@aft.com. You can find it on the AFT website. There's a paper that was published by Fred Moody. I think it was in 2004. I can't remember the conference, but I have a copy. And he talks about the justification for using the shorter time because they call it an effective time. The actual valve closure might be something like whatever, 200 milliseconds, 500 milliseconds. And he gives a justification why you could let me make this, oh, there we go, I can see this much better now. Why the shorter time is an effective time and why you can use that, okay? It looks like somebody else might have published something in here. Force versus time graph showed the peak force is increased with wave steepening, but that the direction of the pressure wave on double pairs as pressure is decreased. How does the reduction, I'm reading the question, how does this reduction in time duration change the resulting loads and pipe supports as calculated with dynamic computer pipe stress analysis? If I'm understanding this right, the results from xStream can give you a force versus time profile. So if you want to do a dynamic simulation with a computer pipe stress analysis, then you can take that force versus time and you can apply it to your pipe loads. But what you would really have to do to get it right is you have to simulate whatever you're trying to do with your dynamic pipe stress analysis. You need to simulate that in a tool like an AFT xStream. It's a liquid, our AFT Impulse software does it. It can put those forces out as output files, and you can import those into your pipe stress software. Okay, so here's another question here, if I can get this. Okay, if the force is only applied for a very short time, does it have significant effect on the pipe's anchors? The answer, I think, is unequivocally yes. You can read about some of those in some of the literature. Back in the 60s, they did some tests on this in the 80s. And there was a lot of experience that in certain cases you could damage anchors, and people were seeing that. So that's why people started trying to do a better job of estimating here. So let me see, what should be the criteria for selection of the line for steam hammer analysis? Well, that's another question, is what's the criteria for doing steam hammer analysis? I mean, the forces are going to be larger, the larger the diameter of the pipe you're dealing with, because you have a larger area. And so, so that's going to be an issue. And then also, the longer your pipe runs, the bigger that those pipe forces can be. Gosh, and I have to apologize here. Is like my tool here. I'm having a really hard time seeing these questions pop up here. It's a very, oh, here we go. Please clarify the wave family also shown in liquid systems. So somebody's asking about how does this apply to liquid systems. Liquid systems would have the same wave family as I was talking about today, but the difference is that because it's not compressible, it's pseudo-compressible with a liquid. But as far as the wave family shape, it doesn't distort. So the back of the wave doesn't catch up with the front, which means that you don't have the same issue in liquid systems you do in gas systems. It's the compressibility of the steam or the gas that causes the wave family to show up. Okay, let me see here. I'm trying to get more in here. Let me see if I got any more questions. Oh, you guys were, okay, sorry, sound, no audio. Yeah, sorry, I got the audio thing figured out here. Sorry, I got that figured out. That was my bad. Someone said that on your liquid surge, you don't have these issues. I don't know about industry failures in force calculations. I just know that if you're trying to do a conservative design, that peak loads are not necessarily trustworthy. So obviously, if you have good safety factors on, then you are maybe not going to see failures, but what that really means is you don't have as much margin in your design as you think. Let me see here, any more questions? I think it's all the questions. So it looks like I got everything. If there's any more questions you have, you're welcome to email me at treywalters@aft.com, T-R-E-Y. Go back to the my first slide here, get my name, and let me get pointer options here. And if I go back to the first slide, my name is Trey Walters, T-R-E-Y. If you put Trey Walters at aft.com, I'll get your emails and I'll try to respond to you. And I think we're just about out of time. So we appreciate all of your attention today, and I hope it's helpful to you, and good luck to everybody. Have a good day.